So we're now going to use this definition here, the one that we derived in the previous lesson, and we're going to use it to find the slopes of some curves at some given points. So as a recap, we found that the slope of a line is equal to the limit of f of c plus delta x minus f of c all over delta x as x approaches 0. We're letting delta x approach 0 so that we can get the 2 points to be extremely close to each other, such that we can find the slope of a tangent line. Right, because the tangent line is 1 point. A tangent line touches the curve at only 1 point. Okay, so our first example is going to be a redundant one, but I'm going to use it to prove it to you that this formula works. Okay, so f of x, sorry, there's glare on this side, so you can't really see what I write on the left side of the screen. Okay. So f of x is equal to 3x minus 1. Now that's a straight line. And I want you to find the point, or rather, we're going to find the slope of the straight line at the point 2, 5. Well, we immediately know that the slope is 3. Okay. But I'm still going to use this to show you that. Okay. So what I would do is I would apply this formula to the case here. So my point is 2, right? So C, my point is 2. So 2 plus delta x minus 2 here, all over delta x. Okay. You get that? So I'm just taking, plugging 2 in for C. Right, now the function begins. Okay, so now I'm going to actually write out what the function is. So the function is this thing here. So going to be the limit of delta x as delta x approaches 0 is going to be 3 times 2 plus delta x minus 1, don't forget this part, minus, well, what is this? F of 2 is going to be 2 times 3 equals 6. 6 minus 1 equals 5. Minus 5 all over delta x. Okay, distribute to 3. So 6 plus 3 delta x minus 1 minus 5, that's going to be 6 all over delta x. Notice that the 6 here and the negative 6 here cancel out. And that once I do that, then only 3 times delta x remains on top. That's going to cancel out with the delta x on the bottom. So I have the limit of 3 as delta x goes to 0, which is just simply 3. Okay, so I showed you that the slope of this line at x equals 2 is equal to 3. So what I did was I plugged in 2, x equals 2, into the formula here for C. I did that. Then I replaced f with the actual formula. So I took this in part and I plugged it into here. And also I evaluated the function at f of 2. Did that here. Then I canceled out whatever I could. And then took the limit of a constant, which is 3. Okay, so that's that. I'm going to show you now a hard example. A harder, not hard, but harder. Okay, so this one we don't know. This is a parabola, so we don't know the slope. Because the slope is different for every point. So I want you to find the slope of this function at the point 1, 7. Okay. So again, I would apply that formula that we saw there. So the slope is going to be, so the slope at x equals 1. Okay. That slope is going to be f. Our point here is 1, right? So I'm going to plug in 1 into c plus delta x minus that all over delta x. Okay. So the next step is to rewrite this using the actual function. So 5 times 1 plus delta x squared plus 2, and then f of 1 is 7. So minus 7 all over delta x. And don't forget to write in the limit, limit notation. It's important that you write that in. Okay. And then, so 2 minus, okay, so the next step is to distribute, or rather to expand this term here. So, kind of annoying, but you have to do it. So, what we get now is, here we go. So it's going to be 5 times 1 plus 2 times delta x plus delta x squared. Okay, delta x squared plus 2 minus 7 all over delta x. Okay, and I can rewrite that as distribute the 5 in. 5 plus 10x, 5 times 10 times delta x plus delta x squared minus 5 all over delta x. Okay. You can see that this negative 5 here and this 5 here cancels out. So what I'm left with is 10 times delta x plus delta x squared over delta x. Okay, so I can cancel out this delta x with delta x here and delta x here. So cancel out, there you go. And what I have left is ten plus delta x. Alright, and once I take the limit, so delta x is going to go to 0, my answer is 10. Okay, so I know it's covered here, but do you see what I did here? So I just took the formula, I plugged in 1, and I plugged in the formula here, and I evaluated f of 1, put that in, and I just simply used algebra. So I expanded this term here, distributed the 5 in, canceled out all my like terms, and in the end I got this. I evaluated the limit that delta x becomes 0, so what I'm left with is 10. Okay, so that's the slope. That's the slope of the tangent line that touches this curve at x equals 1. And it's also the same thing as, it's just a different name, the same thing as the slope of the curve at x equals 1. Right, so I think I have a graph of that somewhere, if I can find it. Show it to you guys. Here it is. Make it simple parabola. I'm going to draw it in. And the point that we had was 1. So that's 1, 2, 3, 4, 5. 1's right there. So we expect the slope to be about 10. Drawing a tangent line there. So that's our tangent line. So the slope of this tangent line is going to be 10. And let me see. Yep, it is. Like, can't really tell from the scale here on the screen, but it is 10. So the slope of this line is 10. Therefore, the slope of the tangent line that touches this curve at x equals 1 is 10. And so the slope of the curve at x equals 1 is 10. Now, instead of finding the slope at one point, I can actually derive the formula for the slope and use that formula to find the slope at all points. What do I mean? So let me rewrite. Okay. So instead of finding it at 1, 7, I'm going to find it at x, f of x. So I'm not going to specify which point I want to find the slope at. I want to be able to come up with an equation that can describe the slope for all points. So first I write down the equation for the slope. Okay. And then what I do is I leave this there, but I'm going to plug this in. So I'm not going to plug in anything for c. In this case, I wrote x. Okay. I'm not going to plug anything in there, but I'm going to replace this function notation with this, with the actual function. So it's going to be x plus delta x squared plus 2. And here, I'm just simply going to write in this thing here. So minus 5 times x squared plus 2 all over delta x. Okay. And then I'm going to expand this thing here. So that's going to be 5 times x squared times 10 times x times delta x plus delta x squared plus 2. I'm going to do that again. Move the paper. Okay. Minus 5x squared minus 2 all over delta x. Sorry, I forgot to write the limit here. Make sure that you keep writing the notation in. Okay, so what cancels out? Plus 2 minus 2. Okay, 5 times x squared minus 5 times x squared. Okay, so here's a way to double check to see if you did this correctly. This bottom term will always cancel out somehow, one way or another. So if you come to a point such that you cannot cancel out the delta x, it probably means, I'm not certain, but it probably means that you did something wrong in the process. So then you have a delta x here, so I could cancel them out. Okay, cancel this, cancel this, cancel this. So what we're left is 10x plus delta x. And if we take the limit, we get, and if we take the limit, we get 10x. Because this thing approaches 0. So we have a slope here. So this is a slope formula. So this formula basically tells us the slope of every point on this curve. So if I wanted to find the slope of the curve at point -2, 32, so if I wanted to find the slope of the curve at -2, 22, all I would have to do is just plug it in. So 10 times -2 equals -20. And if I take a look at the graph here, so -2 is going to be this point here. Let's draw that in. Does it look like -20? Well, this is 10, right? So it's pointing down, that's good. And it looks roughly about twice as steep as this line. So yeah, -20. So instead of plugging in an actual value for x, what I did was I just left it there. I left this there, and I carried on keeping the variable x and not replacing it with an actual number. And if I do that all the way down, I get an actual formula at the end. That gives me the slope for the curve at each point.